This lecture is on section 4.5 of our text, Platonic solids or regular polyhedrons. Two names for the same thing. These are three-dimensional solids. And before we can really understand what they are, we have to go back a bit and recall what regular polygons are. A regular polygon is a two-dimensional or planar figure that has straight lines for its side, a regular for its sides, and a regular polygon. All the sides have the same length, and all the angles are equal in measure. So here is a few of them here. An equilateral triangle, notice every angle is 60 degrees. The sum of the three angles add up to 180, and the sides are of equal length. A square, the sides are of equal length. Here they're denoted by A, and we know that each angle, of course, in a square is 90 degrees. In a pentagon, we have 5 sides. And, of course, you can see that these angles get bigger. These interior angles get bigger as we add more sides. The angles here are bigger. And, in fact, for a pentagon, you can figure this out yourself the way we did in class. Each angle is 108 degrees. For a hexagon, 6 sides of equal length. Every angle here is 120 degrees. Notice we're getting bigger, and these angles for a heptagon with 7 sides will be even bigger than 120. Here's a picture of a polyhedron. I had a nice one that I had clipped offline, but for some reason it didn't appear, so I just drew this one quickly. But you can see that it has, this is not necessarily a regular polyhedron. It's just a polyhedron. It has faces that are polygons. A polyhedron just has, it's a 3D solid with faces that are polygons. Not necessarily regular polygons. It could have some faces that were squares and some faces that were hexagons and some faces that were triangles. And they would not have to be regular. But I just drew a simple one here, and I want you to be sure and know what these words mean. Vertex. The vertices are the points where the faces meet. So we can see this one has 4 vertices. And again, this drawing is off because I had to draw it by hand. The faces are the polygonal faces, and the edges are these edges, the lines joining the vertices. And we're going to learn a remarkable relationship between the vertices, faces, and edges of any 3D figure like this. So a polyhedron was just a 3D solid with faces that are polygons. But we want to define a regular polyhedron. That's what this section 4.5 is about. A regular polyhedron, or a Platonic solid. A Platonic solid is a polyhedron whose faces are identical regular polygons. So that's the first part of the definition. The faces are identical regular polygons. For example, in the cube here, we see that the faces are identical squares, and in this one here, the tetrahedron, we see that the faces are identical equilateral triangles. But there's another part of the definition. the faces are assembled in the same way around each vertex. The faces are assembled the same way. Well, what does that mean? That means, I think this is easier for you to remember. Same number of edges at each vertex. There is the same number of edges, or you could say there is the same number of faces meeting at each vertex. So let's look at our cube. We see that we have identical square faces, the first part of the definition, and the second part, we have 3 edges coming in to each of the 8 vertices of this regular polyhedron. Therefore, it is regular. For the tetrahedron, we see that we have 4 triangular faces. They are all identical equilateral triangles, and at each vertex, you see that there are 3 edges coming into it. So these both are regular polyhedrons. Okay, here we see a picture of 2 polyhedrons. Their faces are made of polygons, 3D objects. The second one I had to draw again. That particular picture didn't appear. So why are each of these polyhedrons not regular? Well, what you see on the soccer ball right away is that some of these faces have 6 sides. They are hexagons. This is a hexagon. This is a hexagon, but this is a pentagon. Only 5. So the faces are not identical polygons. Therefore, it is not regular. Over here, notice that at this vertex, we have 4 edges coming into it, and at this vertex, we only have 3. So 3 edges coming into this vertex, 4 edges coming into this vertex, or 4 faces meeting at that vertex. Therefore, it is not regular. You have 2 parts of the definition of a regular polyhedron. Now, the main purpose of this video is to convince you that there are only 5 regular polyhedrons. And to prove this, you have to keep 2 things in mind. One, that if you build a polyhedron, there are at least 3 faces that have to meet at each vertex. You couldn't build a polyhedron with only 2 faces meeting at a vertex. It wouldn't be, well, I don't know what word to imagine 2 faces here. If you had 2 faces, we could have one face coming like this and maybe another face like that, but you've got to have something fill in here. You'd have to have another face in order to make it the vertex, to make this the vertex of a polyhedron. You have to have at least 3 faces. The total number of degrees at any vertex has to be less than 360. For example, imagine if we took 4 squares and put them together like this. If we took 4 squares and put them together, joining them at that vertex, well, they would lay flat on the table. They wouldn't give us the 3D that we want. So the total number of degrees at any vertex has to be less than 360. This would be 4 times 90, or 360, and you see it doesn't give you a 3D corner. So these 2 things we keep in mind, and we will show that there are only 5 that we could build with those 2 things in mind. There are 3 ways that we could build a regular polyhedron with faces that are equilateral triangles, 3 sides. Okay, so we're going to see that there are 3 that we could build using equilateral triangles. If we join 3 of them, at each vertex, we'll be able to do it. because each angle is 60 degrees, and the total number of degrees at each corner or each vertex would be 3 times 60, or 180 degrees. The total number of degrees at each vertex, adding up 60, 60, 60, we get 180. The octahedron we also get by using triangles. Here we put 4 faces together at a vertex. 4 faces, 4 edges coming into each vertex. Well, you have 4 equilateral triangles, and each angle here is 60 degrees. So we're going to have a total of 4 times 60 degrees, or 240 degrees. And you can see that this opens up a little bit more than this one at each vertex. We have 240 degrees there. How about 5 of them? Well, if we try to hook 5 together, it does work. It's opening up a lot more. You see it's getting a little flatter here. But here we are joining 5 triangles at each vertex. And so we get 5 times 60, or a total of 300 degrees at each vertex. Now, if I try to use 4, what will happen? Well, let's see. If I tried to use if I tried to use 6, triangles, well then I would have 6 times 60 degrees, which would give me 360 degrees at the vertex. And what that would mean was that it would just simply lay flat on the table, and we would not have a 3D corner. So if we're using equilateral triangles as our faces, there is only 3 ways that we could put them together: getting the tetrahedron, the octahedron, and the icosahedron. Now, if we go from the equilateral triangle to the square for faces, then we know we have the cube. We have the cube made with square faces. And notice that there are 3 faces joined at each vertex. And each square here, each square has 90 degrees. So 3 times 90 is a total of 270 degrees at each vertex. If I tried to use 4 squares, if I tried to join 4 squares, well, then they would lay out flat, wouldn't they? We'd get something that just looks like this. Each of these is 90 degrees. 4 times 90 degrees would be 360 degrees, and it would lay flat on the table. We would have no 3D at that corner. So we can't use 4 squares, and of course we can't use 5. That's more than 360 degrees. So we only have 1. We can join 3 squares at a vertex, and that is what gives us our regular polyhedron, the cube. Now let's see if we can join pentagons together, regular pentagons. We know that each angle, here's a pentagon right here, each one of those little angles in the pentagon is 108 degrees. And we have to join at least 3 of them together in order to have a polyhedron at all. So let's see, if we put 3 faces together, if we put 3 faces at each vertex, we would have the total degrees being 3 times 108, and that is 324 degrees, and it's less than 360. So it's flattening out up here, but it is not flat. So it's 324 degrees at each one, and we can do it. So if you fit your pentagons together like this, you get what is called the dodecahedron. Now, of course, we cannot put 4 of them together. If we tried, let's write that, we can't join 4 pentagons at a vertex. Why? Well, because 4 times 108 is bigger than 360 degrees. So, of course, we're not getting the 3D effect. We have to have the total number of degrees less than 360. So far we have 5 regular polyhedrons, 3 made with triangles, 1 made with squares, 1 made with pentagons. And now how about hexagons? Well, notice if we join hexagons, 3 of them, if we join hexagons, we get, well, each of these angles is 120. So we have a total of 360 degrees at each vertex. So we are not getting 3D. In fact, we could tile a floor with hexagons, but we can't join them to make a 3D polyhedron or regular polyhedron. So there are none. And as you go up, heptagons, of course, have angles larger than 120, so we certainly cannot join 3 of them together. So what we've proven here is that there are only 5 regular polyhedrons. And here they are: the tetrahedron, the cube, the octahedron, the dodecahedron made with pentagons, and the icosahedron.